Hi everyone. Today we are going to solve this question that appeared today at the ROS Answers webpage that is asking about how can I move a robot using a twist message. For example, if I'm in a position that we say is coordinate 0, 0 and I want to bring it to the 5, 5, how can I calculate the commands, the twist command belt commands, in order to make the robot move from one position to another? Okay, so this is what we are going to answer here today. And for that, we are going to create a very simple controller. So it's not a controller that requires any map, any obstacle avoidance, just a simple controller that creates the specific commands for moving the robot from position 0, 0 to position 5, 5. We are going to assume that we are talking those positions in a frame of the odometry. So it's the odom frame that those positions, those coordinates are specified. So let's see how we can solve that. For that, we are going to use, of course, the ROS Development Studio that you can access at the rds.theconstructsim.com. So you can create a free account there and start doing experiments like this or programming your robot. Today, we are going to use the Husky simulation. So let's launch it and run it. Great. So take into account that in this exercise, we are not going to talk about obstacle avoidance or localization or else. So we are going to assume that the localization of the robot is actually the odometry value. And in case that you want to dedicate yourself to work with navigation, you must know that odometry contains a lot of error, that it accumulates over time. So it's not a very good resource in order to plan navigation of a robot, but it can be used quite well for other topics. Like, for example, imagine this situation that says I am in position 0, 0 and I want to bring it to 5, 5. So that situation, it's very simple. You can do a controller for moving the robot from that position to the other one. Imagine that the robot is using a camera and is detecting a person in 5, 5 coordinates from the current position of the robot. Okay, then that is perfect. You can use the controller that we are going to develop today in order to bring the robot to that position of the person. Okay, so let's go. Today, we don't need to use the Python notebook, so let me hide it. Here we have this simple simulation of the Husky robot in a closed environment. And for this, today we need to create the first thing that we are going to do is to subscribe to the odometry topic of the robot, so we can know the current position of the robot at any point in time, and we can correct the direction, the speed, and the movement of the robot based on that odometry position. Okay, so let's go. First, let's create a package for that, and let me see. Yes, so we have to go to here, source, then let's create a package, catkin, create a package, and let's call it simple controller. Well, depends on ROS.py. And this is where we are going to put our code. Okay, so here it is, and then in the source directory, I'm going to create the Python controller that we are going to use for controlling this robot. Let's call it controller. Great. So now let's go to the first specify that this is going to be a Python file for the operating system, and then let's import ROS.py. Next thing, so what we are going to do first is to subscribe to the odometry, so we can know at any point in time what is the current position of the robot. For that, then I need to create the initialization of the node that I'm going to call, for example, a speed controller. Okay, and then let's do the subscriber. ROS.py.subscriber Then the subscriber here, the name of the topic that contains the odometry, in this case is this one, odometry filtered, for this simulation for this robot. So odometry filtered is the one that we are going to subscribe to, and it contains messages of type odometry, and we are going to define the callback that it has to be called. For example, new odometry. New odom is easier, simpler. Okay, great. So we are subscribed. For that, we need to import first the message, the odometry message, and then create the callback. Then the odometry message, how do we know? So ROS message show the odometry. The odometry message is composed of this structure and belongs to the navigation message package. So here we have to specify from navigation messages msg import odometry. Great. And now let's define the new odom callback, which receives an odometry message every time. And what is going to do? So this is going to store the current position of the robot, the coordinate x, y, and the theta, the orientation of the robot in the odometry frame. Okay, so for that, let's create 3 global variables. Very simple way of doing it, and that will contain those 3 coordinates, okay, and theta. And let's use them here. And global theta. So we are going to update those variables in this callback. And in order to get the x, so we'll receive an odometry message, and the x position, it's inside the pose position x. So if we have the message, then we have to go to pose position, and then the x. And exactly the same for the y coordinate. Great. Then for theta is something more complex, because the theta is the rotation of the robot in the z-axis, but the orientation of the robot is expressed as a quaternion, so we cannot get that value from the quaternion. Then in that case we have to obtain the rotation in Euler angles. For that we are going to use a function that is called Euler from quaternion, that is provided by TF. So first let's import that function, and let me from TF, it's inside the package of transformations, import Euler from quaternion. Great. Now let's call it. How do we call? Well, the Euler from quaternion will provide us with 3 different angles: the roll, the pitch, and yaw. So it's going to provide us this with this format: roll, pitch, and the yaw is exactly the rotation in the z angle. So we can specify here directly the theta. So we are going to update the theta. In our case, we don't need those roll and pitch, because we are only interested in theta. So but we need to specify them, because we are going to receive that from the function. And then here in the Euler from quaternion, we have to provide a quaternion. Okay, and for that we need to specify every one of the components of the quaternion here. So let me get first the quaternion from the message. So it's from the message, then we have to get the quaternion, that is this one called orientation. So it is pose orientation, and we got it, the rotational quaternion. And then here in we have to specify every one of the quaternion elements in order to call the function. Great. So there we have it. Now we have this callback that is being updated all the time, so we get the x, y, and theta positions updated all the time. And now what we are going to do is to write. So we have to send a position, a velocity command based on the current position and orientation of the robot. So the strategy that we're going to follow is the following. So if the robot is not pointing towards the goal, we are going to rotate the robot in place until the robot is facing the goal destination. Once the robot is facing the goal destination, then we'll move straight until the goal. That's it. That's a strategy that we are going to do, and a very, very simple controller. So let's do the while loop. Not ROS pi is shut down. This is the main loop that will control. So let's first calculate the difference between the current position and the goal position here. And for that we need to define first the goal. So let's say that the goal is a variable of type what? Of type the same as position, that is the type point. Okay, so let's say point, and because of that we need to import from is geometry messages, from geometry messages import point. Right, so this goal, it has the two components of the goal that are the x, that is 5, and then the y, that is 5. Great. Now let's compare here. Let's call it increment of x. This is the difference between the goal and the actual x position of the robot, and the same happens for the y. So by knowing this, we can identify if the robot is facing or not the goal. Then using those two components, we can calculate the current orientation of the robot. This is for and then we are going to compare this current orientation with the actual orientation that we need to get. So in this case, so let's say that the angle to goal, let's calculate first that. The angle to goal is the arctangent of these values. It is the arctangent of the difference between the current position of the robot and the goal destination, and the current in both variables x and y. So let's calculate this arctangent of the increment of y and the increment of x. And arctangent 2, it's a math function that we have to import again from math. So this angle to goal is indicating us how much the robot is not oriented towards the goal. And then what we can do is, if the absolute value of this angle to goal minus the current theta of the robot, if it is greater than a certain value, let's say 0.1 radians, that's about 5 degrees, then we only rotate in place. So we define a speed command. We need to define it here. It's the twist command. It's let's call it a speed twist is 0, 0. So here our speed in the linear value, we are going to set it to 0 for linear because we want it to rotate in place, and then the angular only will have a value in the z component, of course. Let's say 0.3. Remember that I have to import this to its message here because it belongs, twist is a message in the geometry messages package. Okay, great. So if my angle to goal minus the current angle that I have is greater than 0.1, then it means that I have to rotate only. Then also, in case that is not the case, that I'm facing the goal, then I have to do just the opposite. It is the speed linear, let's provide it a value, for example 0.5, and the angular has to be 0. Okay, so then what we need to do is to publish this value in the publisher. In the publisher, this is speed value. We haven't created, and then let's create it here. Top is the ROS by, so it's a publisher to the command belt topic of type twist and with a queue size of 1. Great. Now here we need to provide a rate because otherwise this loop is going to be very, very fast. So let's define here a rate, for example, of 4 Hertz. That's 4 times per second. That, I think that is good enough. And then I'm going to do the sleep here. Great. So we have the program. So the robot is going to rotate until it's facing the goal, and then it's going to move forward towards it. And in order to do that, and to see how it looks, let me open the ARBUS so we can see we can get a clearer vision of how it is moving in the odometry frame, because here we cannot see the odometry frame and we don't see if it is moving on the correct direction based on the odometry axis. Okay, for that I have opened a new shell here, and I'm going to launch the ARBUS. Great. Here it's open, so it's launched, and now in order to see the ARBUS or any graphical tool that you may think of, you need to use this button here that is open the ROS graphic tools. So we connect to the graphic tools, and here we have the ARBUS open with a specific configuration that I have set up in order to go faster. The only thing interesting is here the base fixed frame that I have selected the odometry, but of course we have many others based on that simulation. But the one that we are interested in is the odom frame. It means all the positions are going to be represented from this frame. And also I have included this axis that is showing the fixed frame, that the fixed frame is odometry. So this axis here is indicating exactly the odometry frame, how it looks and what is the position and orientation. We can see now that the robot is facing towards the X angle. That means a theta of 0, and it is located just in the middle of the axis. So it means that its position now is 0, 0 in odometry values. Okay, so let me put it a little bit here. So now we are going to send this program, and then in theory the robot has to move to the position 0, 0. That means sorry, to the position 5, 5. That means 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it has to go towards this direction. Because the robot is not facing the goal, because it's facing this direction, then first it will have to turn and then come in this direction. Let's see if that's what happens. So first let me detach this so we can see everything at the same time, the simulation and the ARBUS. Let me put this on top in order to see everything. And let me also change here the visualization so we can see the simulation here in the front. Yes, that's great. Great. Now, so because of this angle here of the orientation, the current orientation, the robot is supposed to turn on that direction and move there. So because we are not using obstacle avoidance or anything, it's going to crash against the wall. So I'm going to delete them just to prevent the robot from crashing or else. Right? So now let's launch the program and see what happens. Simple controller. So let's see if the robot actually turns and then moves on this diagonal. Okay, we have a problem here with the program. Let's see what's happening. Publish, publish, yeah, here I wrote it wrongly, so it's no, publish, publish here. That's it. Okay, let's change again this and let's relaunch it. And we have a problem here. Okay, it says float object has no attribute rotational Z. Okay, let me see. Oh yeah, here. Sorry, I think I messed it. Here is rotational Q. Yes, there it is. Okay. Okay, and the robot is facing some other place because it started to rotate. Okay, so that's okay because it has rotated too much also. So it will keep on rotating when we launch the program until it faces the proper direction. So let's launch it again and see what happens. Still some problems. Let me see what is happening here. Okay, here there is a point instead of a comma. Here it is. Okay, great. Let's try again. Okay, so far so good. The system is executing and the robot is rotating here and here. Yes, so let's see what happens when it reaches this orientation, because it's the orientation that it has to face and to move forward. Okay, here it is and there it goes. Okay, great. So that is the controller, as you can see. Very, very simple. And then it will keep on moving, of course, forever, because we didn't add any code that stops it when it has reached the 5th position. But this is something very simple that you can do. Okay, so it has reached the 5-5 coordinate and then it keeps on. But of course, now it has moved from it, then it starts to turn again in order to reach the goal. And it's going to stay there forever, trying to go one direction and to the other, to the other. Yes, so it's going to stay there. Great, so that's all for today. I hope you all understood the problem and it was useful for you. Remember that if you want to learn more about ROS, you can subscribe to our YouTube channel and press the bell, please, so you will be notified every time that we publish a new video. We publish a new video every day with different subjects. So thank you very much for your attention and see you soon.